my past work is CTRE, compile time regular expression, and I have typo there, and I didn't notice it, which means it was also on previous conference. Kokuro, which is C++ coroutine wrapper, I presented it here last year. You probably saw it. Also CTHash, I gave lightning talk about it last time. And recently, my day job is hacking Clang compiler. To fix things which bother me. I mean, I got the job to fix things which bother me. Yes. And also learn how actually Clang works because it's interesting. And also, it's preferred in committee if you have a proposal to have an implementation, because if you don't, someone will tell you it's not implementable. And if you tell them, it is, I did it, then they shut up. So how many of you have any experience of compilers or interpreter internals? Andre will do the talk instead of me. Okay, so like 5-ish people. Okay, are you interested in how compilers works in internals? Is it something I should talk today here about? Okay.
Yes.
constexpr. How many of you used constexpr at least once in past month? Great. Good audience. I was afraid. So in Clang, there is a part of the Clang called expr constant. It's Clang C++ interpreter, because if you want to evaluate constexpr, you need actual interpreter. So there is an implementation of Clang as an interpreter inside Clang. It's in one file. And the file has 17,000 lines of code. And it's just semantics for the interpretation. It's not like syntax analysis, it's not like parsing, anything. It's just semantics of the interpretation. Specific only for the interpretation only. Everything else which is usable somewhere else is somewhere else. So 17,000 lines of code. And if you want to change anything, you need to scroll a lot. Up, down, up, down. There is like void void expression evaluator, int expression evaluator, pointer expression evaluator. And there are switches which are long. I mean, thousands of cases in switch. Okay. And it's independent of your CPU architecture. So it's actually emulate your architecture for your target. So if you set have architecture with specific float behavior, it will have same behavior for floats inside of constexpr. So there is also a lot if target is x86, it's ARM, etc. It's a lot. And it's really hard to get into. And I wish someone told me before there are some things which I kind of need to rediscover. And also it implements the whole C++ abstract machine. Because C++ is not targeting any existing architecture. C++ is targeting C++ abstract machine. How many of you did know this? How many of you tried to reinterpret cast pointer to int and do something ugly or jump some? And how many of you got burned by it? I mean, rest didn't raise a hand, light. Okay, it follows expr.constant part of the standard, which is kind of funny part of the standard, which says you can do anything you want in constexpr with exception of this thing, this thing, this thing, this thing. So if you have a paper to add something into constexpr, your wording section is just please remove this line. I mean, most of my papers are like that. So symbolic execution. If you are targeting abstract machine, you are not you don't have pointers, you don't have bytes, you have symbols. Symbols have some meaning, etc. You need to forget about CPU architecture. No longer any registers. There is no stack. There is no heap. Nothing. Did you forget about C++? And the rest of the talk was about JavaScript, but yeah. Forget everything you know about pointers. Pointers is not a value. Pointer is not an address. Pointer is something which points at something. Also, forget everything you know about values, memory, byte layouts. Doesn't matter. You don't need to know that for actually understand C++ and constexpr. So, are you ready?
Yay.
Yes.
Are you ready?
Yes.
Great. So, what's a value? If you are doing symbolic execution, you have value, and in Clang it's called AP value. I ask Clang developers, which are like more seasoned than myself, what actually means the AP, and their answer was like, I don't know. After some digging, it's arbitrary precision value. It can be nothing, none. It can be integer or some number of arbitrary precision. Doesn't need like 64 bits. 30, it can be 48, it can be 256, doesn't matter. It will work for you automatically. It can be some sort of float of any semantics you can imagine, even like for the LLVM, language model people, like 1-bit float. Obviously, it's a thing now. Array, it can be array. Doesn't need to be just normal value. It can be array. Array is a value. It can be structure. It can be union. Or it can be L value, which is pointer. Okay. So what's array? How do you encode array into a value in Clang? I mean, after I will finish this presentation, you will learn. You will be able to hack Clang, and I expect pull requests from you. Okay, is it log? Fine, great. So array is just like 3 values: size, capacity, and data. And data is just a real pointer to some array of values, which it will allocate for you, and you can put values there. It's working. You can put A, B, C, D, etc. Just array. It is capacity. It is size. It's kind of like set vector somehow. It's actually still vector. Union. How do you implement union? Because when you are interpreting C++, you have the AST, you have some value, you have like union is field, which is like by default null because your union is not initialized. There's a union on the right, and if you put initialize the union with integer, its value 0 in the AP value, and it points at the AST node representing int in union. So union in Clang's internals are its kind of variant. Index is pointer to the type or the field, because you can have multiple same field with different value or different same type but a different name. And if you want float, you can do this. And if you want some object, then suddenly it's a struct and it points to somewhere else to a struct. So far, so good? Yes. Okay, fine.
What if in this model in Clang, what if I try to access it as a different type than it is?
It will give you error.
No!
Because constexpr interpreter is defined that it cannot have UB. So you cannot do type panning. Because type panning is UB and you cannot do that. Hence, constexpr C++ is a safe C++.
But my union.
Yeah, your union. No.
Okay, thanks.
You cannot even reinterpret cast.
No.
You can only bitcast. And you cannot bitcast between pointer and value. You can bitcast between maybe some like integers, but not pointers.
No, I'm sad. Please go ahead.
Don't be, it's safe. You cannot hurt yourself. It's like JavaScript. So, what's a structure? JavaScript without package management. Structure is same AP value with which contains 3 values: number of bases, number of members, and data pointer, which points at structure. In this case, we have 3 AP values because we have like structure circle. First is flow structure of base, the position. Can you read it in back? I cannot change the font now, but At least I will be nervous about that. Second is float, because there is a float radius, and color is struct, and it's somewhere else. So this way, client represents internally structure, which means also if you have like deep structures nested, it will be slower. So if you want your constexpr to be fast, you need to have like flattened data structure. It will be faster. Anyway, what's pointer? How do you represent pointer when you don't have addresses, when you have only symbols? And I will. For demo.
Yeah.
Pointer is a thing which points up at something, obviously. And it should work now. It's an address? No, it's not address. It's identifier of you are pointing something. So you can point at null. It can be null. You don't need to point to something, but it's a valid pointer to not something. It's just pointed. It says nothing. You can have initialized object. You can point at it. The object doesn't need to be initialized, and it's still valid constexpr code. You can point at initialized object, or you can point at array. And you can move the pointer inside array, but you cannot go to other objects from pointer to one object. So you can go past the end. That's a special type of a pointer because you need it. So every time you have pointer to object, you can go past the end. That's a valid C++, and it's useful because you need to make it work for iterators and all those stuff. Also, every object, even initialized, can be past the end. Okay, that's pointer, but what's the pointer? Also, there is no symbol ordering because you have symbols, doesn't mean they have any order. So, is it B first or A first? We can argue it can be like descending, ascending. No, doesn't make sense. It can be total random. You don't know. So another thing, before I will tell you what's the pointer, we need to look what's the pointer provenance. It's a magic word people in C committee cannot agree on. So you have structure of the elements int x, I, z, and you have structure with three members. Index 0, 1, 2. And then you have another structure which contains array of the item and another int with count. I mean, it's completely nonsensical example, but and you have like item 0, 1, 2, 3, 7 count. But pointer provenance. What will happen if you have pointer at data 8 and pointer at count? They have kind of same address, even if I told you that there is no address. So this is not valid representation for provenance. You need to think a little bit different. So no. You need to like array is object on its own, so you have like data and count, and array represents only like inner items in it. And then you have another structure like which contains the items on top. First, you get pointer to the object itself. The pointer is the object is somewhere stored. Doesn't matter. And you have pointer at universe T. It's named A. It's somewhere. It's pointer. But you need to pointer to its item, and suddenly it's pointer to A.0. You can imagine as a path from the top object to inner object. And from the path, you can always go only down to maybe to count or to array. And in array, you can go to inner object like this. But there is a special thing for arrays. In arrays, you can actually go to object inside of array. You can, if you have pointer to object in array, you can go to next object or any. So you can move in the array to the right, so like this. So it's a path. it's object A dot 0 dot 0 dot 2 dot 2. And you can do that. You can move pointer inside of the array, or if you have an object to its end, to past one. Past one is marked with like regular expression because I like regular expressions. Yeah. So, does it make sense to you?
No.
No? Who said that? Come forward. We won't shame you, because it's my failure if I didn't explain it to you.
Maybe I have a question.
Uh-huh.
So this means that if I have a pointer to a certain level, let's say to the items data, that means that I can only change it to point within the array or the blunt item after that and nothing else. And the
Or
same goes for any.
You can always go down, but you cannot go up. You cannot. If you have pointer to sub object, you cannot never go back to its own object, with one exception. And I'm not sure if you want to hear it, but if you have trivial object and you have pointer to first member, you can actually reinterpret cast it to its owner. It's a special rule. It's hidden with pointer compatibility. Yeah. It's actually quite heavily used by senders and receivers, and I don't like it, but that shit passed. So you can always go down, and in arrays you can go left to right, or you can jump, but you cannot never go up. And this helps you understand like safety in what if you have pointer where you can go, because if you go up, it's actually UB. Because there can be like virtual table somewhere hidden, and it's like it's not specified how it looks like, so it's at least unspecified behavior. But you can go always down and right and to left.
So basically, if you have array of arrays,
Uh-huh.
and you're down in one of these small arrays at the end, if you go to the next one, like past the last.
If you have pointer to like a member of the sub-array,
Sub-array.
you cannot get pointer to item of the array on top of
So
that.
if you go to the next one, you can only use it like as
Yeah.
a sentinel, and that's
Yeah, exactly. If you have pointer, I mean, in memory, if you think about in like real computers about memory, then yes, it's just next address. But it's C++ abstract model doesn't allow that, because there can be some padding between. You don't know. It can be some like there can be some virtual table, and you never know.
So it's undefined behavior.
Yeah, there can be some also rendering. I'm not sure if it's undefined behavior, but it's definitely unspecified.
Okay.
It's a difference. After a few beers, we can discuss that. So, do you know about L value and R value? You probably heard these like terms, and they are confusing, and actually they are obsolete now because we have X value and to R value and pure value. But let's say we have L value and R value. What's the difference? One is on left and one is on right. L value is L value, R value is in terms of the abstract machine and the constexpr machine. It doesn't matter. It's just different type. R value is just a different like type of reference, which tells you something. I will get there soon. So it's mostly marked as like used as this thing is temporary. You can steal from it. This is like my personal model how to deal with R values. This thing will go away. You can steal. No one will notice. So lifetime, because we need to think about lifetime now. There are global variables. You can have global variables even in constexpr, but they are immutable. But you can even access non-constexpr variables in constexpr if they are static. You cannot access their value. You can have pointers to them, and if they are const, you can actually access the value. You have scope-based variables which are like LIFO, like last in, first out. It's like how it works. Temporaries. Every time you do something in expression and you don't have name for it, it's a temporary. And you can have also custom lifetime, which is heap allocation, but there is no heap. Sorry. You can allocate something somewhere, and then you are actually in charge of the lifetime. So it can. Also, temporaries can get lifetime extended, so it's actually like this. It's not pyramid. I want it to be pyramid, but it's not. So, identifier of the thing you are pointing at, its location. So global variables are identified by its name. So if you have like global variable, then it's just name of the, and the pointer will like point at name, counter, file, or whatever. Local variables are identified by AST node, which is also a name, and also its version. And version is how many times you called something. It's a counter. So the virtual machine actually knows that you are not using value from previous evaluation, because it can be there still. And you can allocate memory since C++20. And for that, you will get unique key, which is actually just integer, which increments every time you allocate. But you cannot observe it. So what's the pointer? We are back. Let's say I have two values, integers, 10 and 20. It doesn't work. And I have like this code. It's like coordinates variable. Oh my god. No, it's correct, because sometimes I'm also coding in JavaScript. I did this animation engine in JavaScript, so sometimes I'm like mistaking C++ and JavaScript now. So it's correct. We initialize the coordinates variable with x, 10, epsilon 20, and point at x in it. So the pointer, it's two things. It's a L value base and provenance. The L value base is different based on what you are pointing at. This time it's a stack-based variable, so it's pointer to var declaration, which is just pointer to AST. So it's this variable. From there you can actually get its type and everything you need for evaluation, and version. Inverse code is 0, index code is 1, 2, 3, etc. And that is provenance. Provenance is just pointer to path. Here it's just path of one element. We are going to subitem 0, so we are going to x. That's pointer. So each pointer during constexpr evaluation actually allocates. Surprise, surprise. So you can also move to other item just by changing the provenance, obviously. So if we want something, it doesn't work here. If we want have allocation, like let's say fixed string of 16 characters is useful. We can allocate, and then base is the different type of same size, because they are actually stored inside of the AP value. So this is actually not allocation, but the path is. It's pointed to expression. So every allocation holds value where it was allocated. So if you leak it at the end of constexpr evaluation, it will give you error. You're actually leaking. This is not valid constant evaluation, and you need to fix it. So constexpr interpreter won't ever leak. And also allocation ID, which is just number. It's actually random here on slides, but so. And provenance, if you are like having pointer to fixed string itself, it's null, it's empty, because you don't need to go anywhere. But if you want to go to subobject, then path is 0. And if you want to go to subobject of the array, you need two items, and path is 0, 2, 0, 3, etc. And there will be 16 elements like this, and you can have pointer to allocation. But it always tracks the original object. So in this world, there is no like object next to your object in memory. You cannot count it because it doesn't make sense. It's somewhere. And if you are looking past the array, obviously it's special pointer past the array, and it's still valid. And if you have static variable, 42 obviously. By the way, Japanese programmers are delighted by usage of 42 as a random number everywhere. Anyway, you have only one base which points at the var declaration, and inside of the var declaration is even the value 42 stored. And provenance here doesn't make sense because it's just integer. So now you understand how pointer looks as a symbolic inside calling. And where are values stored? Because you have like, and you need to store the values somewhere. So global table of variables, if you have like static variables, because compiler later needs them and put them in your binary, so they are stored in some table already. Local variables are like stack-like data structure, actually is stat map. And allocations are stored in also stat map, but with index of the allocation. It's simple. And because it's using, there is a fourth type of pointer which I didn't put here, it's pointer to type info. Did you ever use type info?
Yes.
Okay, quiz time. Do you know 3 ways how to throw exception in C++ without using throw? First is operator new, can throw. Second is dynamic cast to reference. It can throw. And type info, if the type info is not present in the library, then it can throw. I was surprised when Core told me. I have proposal about exceptions. So yeah, and we have like 4 types of pointers, and they're actually using pointer tagging to store type of the pointer inside normal pointer, so it saves some space. And I wanted to add another type of pointer to exception, but I couldn't because there is no space. So yeah. So a constant evaluator, you have AST, and it just follows the AST as the most primitive like interpreter you can think of. There is no bytecode. You have just tree, and you are evaluating it, and you are evaluating. So if it's if, and so you evaluated the expression, condition, go left, right, and that's all. That's how constexpr works. Okay, and this is all implemented in C++. And it's confusing, because sometimes to implement something in the interpreter, the best feature for it is actually the feature you are implementing. You want to implement coroutines, you need coroutines. You want to implement exceptions, you need exceptions. Yeah, but it helped me understand how C++ abstract machine works. And because the machine is like abstract and everything is like checked, it can detect most of the UUB. There are some like cases where you can actually get away with it. So you can actually say that constexpr C++ is safe C++. Because you cannot like have like stack overflow, because there is no stack actually. You cannot like take pointer and go somewhere else. You cannot do integer overflow, because integer overflow is not defined. So most of the standard library, because it's just C++ we are evaluating, most of the standard library should be constant evaluable. Do you agree with me on it? Because if we don't agree, I can't continue. I mean, constexpr C++ is just subset of C++ which is safe, and standard library should provide you everything, all the tools to be usable in constexpr. But most is not. I mean, I can understand like I/O and observation of like outer state like time or network. Do you want networking in constexpr? I don't. So there was actual proposal in Prague meeting from Sean Baxter to change the model of interpretation, which allowed you actually load any shared library during constant evaluation and call any function from it. How many of you think it's a good idea? Why? Please stand up. Please stand up and tell us.
It's a delightful way to troll people.
And it's also a delightful way to like have like source code malware. Because you can suddenly you can just use networking. You can spread your like malware across the internet.
We can introduce it.
I mean, Rust templates and like compile time programming is weird. Do you know how it's implemented in Rust? You probably know.
What do you mean?
Like compile time programming and like all the like modification of the code and reflection and stuff like that.
I think I only know how to use it.
Okay, so story time. There are two Rust compilers. One is the Rust itself, and someone wrote the Rust in Rust, to actually allow you to do the like modification and template programming in Rust. And it works like this: you mark something with some annotation. I don't know the right term in Rust. So like this should do like there should be some like change, and what Rust compiler will do will give you token stream to library which implements the Rust compiler itself. Do the ST parsing. You can do whatever you want, any change, and it will spill new token stream which is again parsed by Rust, and so if you have multiple annotation, you can go like n square.
It's one of them. Then you have the const. That's right.
Awesome. I'm not a Rust person, but this is funny. So quiz time. What containers in standard library are constexpr compatible? Shout, please. Array.
Yes.
Yes. Okay.
Are you sure? Yes, but not array of size 0 in MSVC because of VI, I think. DQ. How many of you know about DQ? Did you use it? DQ is awesome. Nope. Ah, it doesn't work here. Nope. It's not constexpr. Flatmap. Flatmap is new container in C++ 23, which is using underlying storage with vector, and you can have like cache-friendly map container. It's actually using two vectors, one for keys and one for values. No. 23. No. Flatset.
Oh.
No.
Obviously no. Forward list.
Ah, maybe.
I mean, everyone knows how to implement it. It's just linked list. One way with linked list. Is it constexpr?
No.
No. Why? In place vector. New thing in C++ 23 and 26 it will be, I think.
No.
You don't know.
Yes.
Sometimes. You can use only trivially constructible types in constexpr because it's based on an array, and if you put it on stack, you need to initialize all array members, and if the type is not initializable, then it cannot be constexpr. We are trying to fix that, but we cannot agree on how. Hive. Did you hear about Hive? It's kind of like a non-contiguous vector which guarantees pointer stability. So if you create a put object there, it will stay always on same address. It's really useful for game development and networking. And also the paper is, I think, the highest revision paper in the committee, 28, I think.
It's dynamic, it can be.
Why cannot dynamic containers can be constexpr, by the way? You can allocate in constexpr.
Obviously, they are not.
It's not, because author just decide to not do constexpr implementation. I mean, I can understand because he is from game dev and he doesn't care. I think we need to cut this out. But list. If you don't have forward list, then no. So map.
No.
No.
No, I'm sorry. Optional. Optional is a container since C++ 26 because it has begin and end.
Yes.
It allows you to have like a range of optionals, and you can flatten it and concat it, and it's useful, but some people are disagreeing with that. It's constexpr. Set.
No.
It's same like map, it's not. Basic string is a container. People are using it as container.
Yes.
Yes.
Yes, C++ 20. Unended map,
No.
nope. You can see the pattern now. Under the set, val array. You don't know, you are not sure because you never use val array. No one used val array. It's like the meme, Mom, can we have simmed? No, we have simmed at home. No. Vector.
Yes.
It's allocated, yes. And string is also allocating and it's constexpr compatible. Interesting, isn't it? So let's look on some containers in detail. Array. Array is just number of like items. You can have past the end. No, it's just simple. They need to be initialized. So you cannot put an initialized member if it is on stack. Just array. Vector. Vector is just 3 pointers. Begin, and you have like some storage, and you can, because it's allocated, it can be initialized, and you can put their stuff there. And once you are on the capacity, you will allocate bigger container, and you will move all the information from there. This is move out state, by the way, and switch the pointers and reallocate the vector. It's just vector. Everyone knows how vector works.
You will be surprised.
Okay, yeah. Yeah, probably yes. So, and again, you need like bigger storage. All sane implementation are allocating 2 times more. MSVC is not sane implementation. Yeah, we cannot publish it. And yeah, you can fill it and vector. You can you have list. List has like front pointer, back pointer, and size, which was actually breaking ABI in GCC 5. So that's why people didn't like coding C++ in Red Hat for a while. So
They like it.
now, I mean, now CentOS is dead, and Red Hat already like decided it's on. They are already on new ABI, but CentOS 7 was still on the old ABI. I mean, if you didn't hit this bug at least once, like in half year, who are you? So like.
I hit so many bugs that I don't remember.
Okay, stat list has like some node, and you put their value A, and if you do pushback, it will create pointers accordingly. And again, you can do push front. So it's O1 operation, and you can also like erase item from the back, from the front, and also from middle if you have iterator on it. It's just working nicely. By the way, the easiest way how to visualize data structure is to implement it. Yes. In place vector is just array with number of items in it. So you can actually put the content, but because it can be on stack, it needs to be initialized. So it is constexpr only for some cases, not for all of them. The queue. I didn't animate this because I'm kind of out of time, but the queue looks like this. It's pretty cool. I actually, when I was implementing it, I didn't know that. I thought it's just like linked list with bigger nodes, but actually it's a vector of indices with pointers to leaf, which are of fixed size, and you have prefix space and suffix space with defined capacity. You can like there's some capacity, and you can put in front, in back by O1, and in middle as in vector. It's wonderful data structure, and libc++ gives you each leaf will be 4 kilobytes, or at least 16 items, whatever it's like first. MSVC, do you know what the size of the leaf by default?
Small.
16 bytes. So you basically have like vector of like allocations. So yeah, don't do that. So, but this all seems implementable. Why they are not constexpr?
They were not implemented.
Why is only vector and string constexpr?
Reflection.
Reflection, what? I'm confused now.
For the purpose of reflection?
No, it was in C++ 20, and it's because of chocolate.
What?
You are confused. There was a last slot for C++ 20 cutoff for like wording review, and I bribed a chair with a chocolate. Yes,
So you write
it's intentional crime, by the way. But the language is improving with every C++ version, and every C++ version gives you new features, and we are slowly growing because C++ committee is driven by volunteers, and if you want to do change, you need to do it because no one else will do it because they don't care, probably. So there are some limitations for constexpr. Another quiz time. Atomic operations, can you do it in constexpr?
Why not?
Currently you cannot. It doesn't work here. You cannot do it in constexpr. But I mean, you can see that it actually makes sense to have atomic operations because constexpr C++ is just single-threaded C++. So you should be able to do atomic operations, but no,
Can I have threads in constexpr?
not yet.
Do I need to make operations?
Yes, you can. You can use atomic operations if you don't want to duplicate your code because you have like algorithm, maybe like some function which takes one item from some data structure, process it, and do it. And if you don't want to duplicate code, you want to use same code in constexpr and in the runtime. Because atomic is a type, you cannot just if const eval it. You need actually maybe some templates, or you can just make atomic constexpr work. Changing active member of union. Yes, you can do that since C++ 20. It will destroy, you need to destroy it on your own, and then you can change it to another member. You can you use control flow like if, for, and while in C++?
Yes.
And do you know from which version?
14.
17?
Did I hear 16, 20,
17?
14.
14? By the way, C++ 23 was released on this Monday, and it's officially called 24. Exception throwing. Not yet. Correct. Lambdas. Can you use lambdas in constexpr?
Yes.
Do you see any reason why they shouldn't be like usable in constexpr? Because it's C++ 17 feature, and it's just devoting, just allow them because like there was a list of things you cannot do, and with each version we are removing one star. Trivial default initialization. So you actually don't need initialize every variable in constexpr code. Can you do it, or you do need to initialize every time? I mean, everyone is doing safe C++, so we are initializing our variables, but in this case we don't need to, and since C++ 20. Try catch. Can you have try catch inside of constexpr code?
Yes.
I mean, raise hand if you think yes, and if you don't, then don't raise it. Okay, like 6 people says yes. Yes, you can do that, but catch will never be evaluated. C++ 20. Unevaluated inline assembly. Can you put assembly block inside constexpr function?
No.
No.
Yes, you can, but you cannot evaluate it. Because in past, constexpr model was a little bit different, and committee tried to like make constexpr. If you mark something constexpr, then everything there should be constexpr evaluable. And like around 20, we changed the model that some part, and in 23, maybe even no part can be constexpr. So that is like different philosophical model now. Usage of variables. Can you use variables in constexpr? It's kind of spoilering because you can initialize them, so you can probably use them. In that respect, it should be different order. Yes, since 14. Can you use byte array as an object storage? So you can actually like do in place new and put object into byte array. How if yes, can you tell me how it should work with the AP values so I can implement it? No, but I want to somehow make it, but we will get there. Can you use valid cases for reinterpret cast? Because reinterpret cast is kind of like utility of cast. You put there everything you don't know, you don't have any name for it. There's like you can do reinterpret cast between pointer intercommentable pointers. You can pointer cast between bytes and objects, and you can reinterpret cast between trivial member of trivial object to the trivial object, and also I think also like integer floats or something like that. But, yeah.
No.
No. Can you use virtual bases? I mean, how many people here use virtual bases because I want to talk with you?
For what?
I mean, you're a trainer, so for training, yes.
Obviously.
This is training, and you shouldn't use it, but yeah. So, is it constexpr?
Yes.
No, it's not.
Mm.
Can you use virtual functions? And now we will be voting because I'm not sure how it will go. So, those people who think you can use virtual functions, please raise your hand now. 2 people, 3 people, 4, okay. Jakub, what do you think? Yes, since C++20 you can use virtual functions. By the way, if we want to make IO streams, constexpr, we need to also make virtual bases work. Don't ask. So constexpr obviously needs some improvement. But I have like title of this talk, my favorite data structures. Can you guess my favorite data structure?
Thank you.
Thank you.
I was thinking about it before, but no. There's a data structure which is not in C++ standard. And it's also motivation for like me changing constexpr and having this talk.
Ring buffer?
There is a proposal about ring buffer which actually like does memory mapping under the hood, so you can actually do like quite fast ring buffer, but no, not ring buffer. That's too easy. It's called HMT. Did you heard about it? Andres heard because I'm going to lunch with him obviously every week, so he knows about it, but everyone else? This is the most awesome data structure ever you heard of. Hash, array, mapped tria. It's all the, it's like a cloud and blockchain and LLVM of data structures. And it was invented in 2000, and 2011 there was like another variant of it. It's new. And it's cool. It's one data structure you should be using. And I show you how. We have root on the top, because hash array map tree, so it's kind of like tree, but also like a hash table. So you have root and you have value on the top, and there is a hash of the value 488 f, like 16-byte hash in this case, because I want to make it a little bit smaller, so I'm using 16-byte hash. The value doesn't matter, but it's there. It's just some sort of leaf value we want to search for. And the premise of the data structure looks like this. We have level 1, and the root points at the level 1 of the data structure. And first 4 bits of the hash is used to address member in the array to choose a pointer to next level. So in this case, it's 4. And in next level, you use next 4 bits to select another level, E, and 8, and then F. So technically, you can see it's O1 for searching, inserting, deleting, modifying, whatever. But it's getting complicated, obviously. You can have like multiple things there, not just one value, obviously. Also, because it's a hash table, You can also have like values which are not on the final level. If there is no conflict for your value, you can put it in higher level. But for that, you need one feature in a language which C++ is missing, and I want to get it there. You need pointer tagging, and also you can have in level 1 a value. And you can have also multiple values if they have same hash, because it's a hash table. But you need pointer tagging. So you actually mark all the pointers which lead to the values with tag 1-bit information. And every other pointer there is tagged with 0. So you will look at the 1-bit, and you know that next pointer is next level, or actual leaf values. It's cool data structure, but it's get better. There is a lot of nulls, and you don't need them because it's like a lot of overhead. So you can compress it, and you can put bitmap, which actually which values were used. For that, you need feature of variable length objects, which is already in C++, but only for runtime, but not for constexpr. Here it's just one item, so there is only 1 bit. Here there are 4, so there are 4 bits. It's cute, isn't it? Okay, but it gets better. Let's change root to atomic pointer. See what I did here? And in front of every level, with the exception of level 1, you need to put another atomic pointer, and also in front of the values, you put atomic pointers. And then you change the pointers to atomic pointers, and suddenly you have a log-free data structure. And you can access it from multiple threads. You can exchange it without locking. But it gets better. Let's throw away atomic pointers and introduce ref count in every leaf, and also in every level in every leaf. And suddenly it's a persistent data structure. It can share, you can have multiple copies which will share a common element. So you can create a new level 1 which doesn't contain the value 0x7 because you delete it. And you can have another copy which has only like this one node different, and everything else is shared. It's persistent data structure, so you can actually have multiple versions, and you are not allocating much. So you can have transactions, you can do modification, and you have multiple versions, and then you atomically change, and you have like the latest version, and it's cool. But it gets better. Let's forget about ref count for a while. Actually, yeah, almost. And we can actually not use pointers. We can use flat. We can use offsets, and we can put all the data nodes and values and leaves into flat storage, into file. And we just use offsets instead of pointers. They are smaller. And you can change the data structure just by appending. So if you have this subspan of the file, you have old version snapshot, which is immutable, and there is another version. This is my favorite data structure.
I have a question. Do you need pointer tagging if you do this?
You need you don't need pointer tagging, but you need some sort of information in the offset. So let's say that it will always be aligned at least by 2, and you will use the 1 bit for the information if it's a leaf or not. Otherwise, you will have multiple levels which are not necessary. So do you want to have like, usually it's used like 32 bits hash. Do you want to have 8 levels or 1 bit? It's up to you, but I prefer 1 bit. HMT gives you O1, insert, search, and delete. Modification 2. It grows like tree and not like hash table. So it grows slowly. You don't need to allocate big block and big block. You don't need rehashing. So it's predictable. It's like deterministic more. It can be modified to be log-free. It can be modified to be persistent. And it's usable in flat storage. before I left in Avast, I wanted to use for various definitions. But you cannot implement it in C++ if you want to be in constexpr 2. You need pointer tagging. You need variable-sized objects. This can be kind of avoided if you allocate arrays and put bitmap into array, and you will waste some bytes based on the size of the pointer, but it can be avoided. You need atomic operations if you want to be log-free or ref counting. You need byte storage for objects if you're doing the flat storage version. And yeah, that's all for the HMT, and constexpr will get better. We are going to have another meeting. It will be in less than a month in Wrocław in Poland. And if you want to go there, please talk with me. I can invite you to the system. There are some papers which will be there. Not all of them. We have like 152 papers in this mailing and probably 50 more from previous meetings. So there will be things which will not make it into 26 because this meeting is C++ 26 feature freeze. So first paper is allowing exception throwing in constant evaluation. It's mine. And I implemented it, and it was kind of funny, and I implemented it out of sheer hate because they told me it's hard to implement and we shouldn't have exceptions in constexpr because some implementers don't see usage for that. I don't know.
Kudos for that. This is really a really valuable one.
It's really valuable, and you can actually put it into Spinae, and you can get nice error messages out of it. You can have like a template which cannot instantiate because it throws exception, and it will actually the wording doesn't contain it, but my implementation will access .wat member of the exception type, and it will print it as a nice error message for you.
I like it for semantic types, like when you want to enforce, narrow down the amount of values a variable can get in compile time, and tell the user, hey, you are going out of bounds for that.
You can use it as contract violation.
Yes, exactly.
But we are getting contracts for that also, but yeah, hopefully. Constexpr exception types, because if you want to throw exception types, you need to make them constexpr, which turns out just marking them all constexpr, and then be really careful to not break ABI. Because in libc++ and libc++ ABI, constructors of the exception types are in libc++ ABI, but what members are in libc++, so you need to be careful. Constexpr atomics and atomic ref types, there's a paper for that, also mine. I mean, most of them are mine, but constexpr stats shared pointer, this one is not mine, this is like Kate, I cannot remember surname. But yes, we will get shared pointer also in constexpr, because they argued that you cannot do it because it contains atomic. First revision was to just make if const eval and do the counting manually. It's like heck, but now we will have atomic operations, so you can just make it constexpr and it will work. Constexpr pointer tagging. How do I make pointer tagging if I don't have address? I actually put into a value base metadata, and actually I have 64 bits for tagging as I want. And it works, and hopefully it will get into standard. Trivial unions, that's from Barry Revzin, which allows you to make in-place vector constexpr, because it allows you to have initialized values in trivial union. So you can put, you can actually make lazy initialization and destruction, so it won't be RII, but you need to care of it on your own. Constexpr containers and adapters. This paper makes all the containers and adapters constexpr, obviously. With exception of Hive, because when I was doing the wording, Hive wasn't there yet. So Hive will be only a container which is not constexpr in 26. Freestanding constexpr containers and constexpr exception types. This is interesting for automotive, because you can use, with this, you will be able to use vector and stuff in constexpr, but not in runtime. So if you do metaprogramming, which kind of happen in embedded space, but it will be, so it's marking like vector const eval and not constexpr. So you can have it only there, but you cannot have it in the runtime. So you can guarantee that your code is not allocating anything, but for like reflection code or stuff, vector will be there and exceptions will be there. constexpr coroutines. This is my favorite one. And actually the wording is super simple. I can actually show it to you. At the end. constexpr stat format. It should be constexpr. constexpr stat generator. Because if you have coroutines, you want the generator to be constexpr too. This is paper from Jeff Snyder. It's just draft because he didn't he missed deadline. But this paper allows you to transform constexpr allocation into anonymous constexpr static object. So you can actually return vector of strings from a constexpr function and it will work. It's cool. I saw it yeah. You can return map of values and all the allocation, all the nodes, it's just anonymous object put into your binary, and the other part, the prop const, is propagating constness, so you can actually see what's const and what's not, and it's magic. This is Herb Stutter's paper, because everyone talks about safety, even CIA and Department of Energy in the US and White House is talking about C++ safety, so we should too. And this paper proposed that by default, if you want safety, your C++ will have same behavior as in constexpr with all additional checks and safety checks. So you can actually create safe C++ if you actually really need it, and if you don't care that much about performance. So you should have the option. And because constexpr itself is safe, so it's actually the paper argues it's the right model for you to use. And yeah, that's my talk. If you want to see the wording for the coroutines, I can click it here. Because every paper should have wording. Oh, I don't have internet here. Okay, I will show it to you on my laptop on break. And this is all. Thank you.